planet is 4.5 billion years old. But how do we know that? There are no tree rings to count. No organisms of any kind go back that far. And even the oldest rocks on Earth are too young to tell us when it first formed. So to find the age of the Earth, we look to space. Space rocks, that is. 4.5 billion years ago, our solar system was a whirling disk of hot, collapsing gas. As the disk cooled, minerals began to condense from the gas. And eventually, all those little bits and pieces were swept up to become all of the solid bodies of the solar system, all of the planets, the comets, the asteroids. Some of those very first solid particles have been preserved, almost in their original state, and hand-delivered to our doorstep as meteorites. So we have the oldest materials in the solar system at our fingertips. But how does that help us tell how old they actually are? That's where radioactive elements come in really handy. So take lead, for example. A lead atom has to have 82 protons, otherwise it's not lead. But the number of neutrons it can have is a little more flexible. There are 4 naturally occurring types of lead, and these are called isotopes. One of the 4 can only be made in a supernova, when a star explodes. The other 3 can be made that way too, but they also can be produced in a second way. They're the products of the radioactive decay of uranium and thorium. This decay happens at a steady and predictable rate. So as time goes on, the amount of these radiogenic types of lead is increasing. And in the 50s, for the first time, we were able to take that information and back out how old our meteorite samples were. And that's the age of the solar system. So voila. There are lots of other isotope systems that work in a similar way. So actually, we can use the same technique to date all kinds of different rock samples, which is really useful if you're trying to figure out what happened when in Earth history. But what about the rest of the solar system? We went to the moon and brought back rock samples, so for a few places on the moon, we actually have a very good idea what the age of the surface is. But everywhere else, not so much. If you look closely at the moon, I'm sure you've seen pictures, you know that it's absolutely covered with impact craters. That, it turns out, is really useful because we can compare the density of craters on different surfaces to start to figure out which surfaces are older or younger than others, because the older surfaces have had more time to collect craters. So we can put together a chronology based on relative ages and tie that down in specific places with the meteorites or the rock samples that we have brought back with absolute ages. And even better, we can take what we've learned about the moon's cratering history and use it to understand the distribution of craters on other planetary surfaces, like Mars or Mercury, or even the rocky and icy satellites of the outer planets. So if we have rock samples, we can get absolute ages. If we have craters, we can get relative ages. And by putting them together, we can start to keep track of time in the solar system. Thank you.